Hello everyone, welcome back to the channel. We are back again with another PoD solution video. In this video, we are going to be discussing the problem togetherness of a family, a very interesting tree problem. So let's get started. Alright, so let's start by reading the problem statement. So the name of the problem is togetherness of a family. It states that in the world of Magic Land, there is a park in which a group of people are playing a game. Every person in the group is a child of one another person in the group except one person who is the parent of all the people in the group. Here each person is represented by number, that if there are n persons in the group, then they are represented by numbers 1 to 7. Okay. And the direct and indirect child relationships. Okay, so it's telling me the kind of relationships there are in the park. So I mean, it's the same kind of relationship that exists between me and my grandfather have indirect parent-child relationship, while my parents and my grandparents would have a direct parent-child relationship. So something like that only. And then everyone is given a token and we are asked some queries. In one query, a number representing a person is given and it is asked to find the number of direct and indirect children of the person who have prime number in the token given to them. Alright, so for more clarification, see the example below, and I have an example. Okay, 1, 2, 3, 4, 5, 6, 2 queries. Okay, all right. All right, let's head to the next section and analyze this example before we jump into the solution of the problem. All right, so let's discuss the example of this problem. The example that we have is we have a structure something like this. So we have the token values given first, which is 1, 2, 3, 4, 6, 7, and then we are given relations something like this: 1, 2, 2, 1, 3, then we have 2, 4, 2, 5, 3, 6, and 3, 7. So if we try to draw the hierarchical structure that we have from the given data, it will be something like we have 1 has children 2, and I'll just again correct this. I'll write this properly. We have 1, 3, right? So now we have 1, 2, 1, 3, then we have 2, 4, 2, 5, 3, 6, and 3, 7, right? And we have token values associated with all these. So with 1 we have 1, with 2 we have 2, with 3 we have 3, right? It's given in that way, right? Corresponding index. So we are asked now, the query is given to us is, let's assume we have different queries. So for every node, let's try to answer what's going to be the number of children who have prime number tokens available, right? So let's start with 4, 5, 6, 7. Let's then drill down to 2 and 3, and let's then sum it up for 1. So for 4, do we have any children for 4? No, right? So for 4, the answer is going to be 0. No children of 4 have prime number values, right? Similarly for 5, answer would be 0. Similarly for 6, answer would be 0. Similarly for 7, answer would be 0. Now we come to 2. For 2, if someone asks me 2, then for 2 I have 4 and 5 as its children. So 4 is not a prime number, 5 is a prime number, right? So for 2, and then we ask all its children, all the children of 2, 4 and 5, like, tell me what all values of your children are prime number, right? So 4 has 0, 5 has 0. In 2, what we do is, so for 2, the children of 2, which is 4 and 5, out of them 1 is prime, so we add 1 plus their children's values basically. So like 4, how many children does it have which have prime values? And similarly, so 4 has 0 plus 5 also has 0, so the answer for 2 is 1. Similarly for 3, we have 6 and 7, out of them 7 is prime, so we have 1 plus the answer for 6 and the answer for 7, which in both the cases 0 here, so we have 1, right? So now come to 1. So 1 has direct children 2 and 3, right? So 2 is a prime number, 3 is a prime number. So we have 2 plus the answers of its children, which is the answer of 2 plus answer of 3. So answer of 2 is 1 and answer of 3 is also 1. So 1 plus 1, which gives 4. So right. So can you see a pattern through this example, that we go down through the tree and then we come back up asking every children what's your answer, and then pushing it up and then summing up it at the top. If that makes sense, hit to the next section, because we are going to use a lot of recursion and the tree structure. So it's going to be very interesting. Let's go to the next section. All right, so now let's try to understand the logic behind the problem by breaking it down and then solving each and every part of the problem. So I'll just quickly draw the structure that we had. 1, 2, 3, 4, 5, 6, and we had 7, right? And let's take the input that we have. So in the first line we had n, which is number of people, and then we had all the token values, right? So here in this case it was 1, 2, 3, 4, 5, 6, and 7. All right, and then now we have n minus 1 relationships. So it's an important property of a tree. Why? Because in a tree, when and the question says that everyone has one parent, right? And everything has one final parent, which is the root node basically. So let's take a real life example of why when we have n nodes, we have n minus 1 edges. So take an example of your relationship with your father and your grandfather, your grandparents. So you are 3 people, your parents and your grandparents. But how many connections exist? The connection between grandparents and your parents, and the connection between your parents and you, because every node has one parent, right? So whenever there are n nodes, there are n minus 1 edges in a tree. That's why we have n minus 1 connections. So we have connections 1 to 2, 2 to 4, 2 to 5, 1 to 3, 3 to 6, 3 to 7, and so on, right? And as we discussed in the last section, we are going down and then bubbling up with the solution, right? So we need some kind of way to go down and then come up and basically aggregate all the solution, all the values from all the child elements, right? So let's say we start from 1. Let's say we start from 1. Okay. So let's see, for all the children of 1, what I'm gonna do is let's go down to any of the children of 1. Let's go down to 2. Do the same thing for 2 as well. Go down to any of its children. Come to 4. Do the same thing to 4 as we did to 2 and 1. But do we have any children for 4? No, right? So now we start coming up from 4. So now when we come up at 2 has another child as well, which is 5, right? So we start with, again we go down on 5 and do the same thing again with 5, but 5 does not have any children, so we just come up to 2. All the children of 2 are covered. Now we come to 1, right? Now with 1 we had another child, which was 3. Do the same for 3. We have 6 and we go to 6. There are no children for 6, so we don't go down and we again go back up. And then we go down on 3 is another child, which was 7, and do the same for 7. We come up and then again all the way to 1. No more children. So our basically the traversal is finished. This is what is called a depth first traversal. We go to the depth first, come back, and we go to the depth first and then come back. We solved another problem, LinkedIn connection, in which it was breadth first, right? So we would span across all the child nodes on the given level, right? And then go down. So it was broad. This is deep. So it's called depth first traversal, right? So we are going to use depth first traversal and also the logic to compute and check if any given token is prime or not. And in the next section, let's first discuss the logic to check if a number is prime or not, and then we'll go back and dive into the implementation of this logic. Let's talk about a logic to check if our given number is prime or not. We're going to talk about a logic which is slightly better than the logic that we have studied till now, namely the logic, to run a loop from 2 to the square root of the given number and check if any number in that range divides the given number or not. We're going to make some observations, and based on that, we are going to devise this slightly better algorithm. So let's see. So suppose I have numbers, let's say given a number n, I'll say if n is less than equal to 1, I can surely say that it will never be prime, right? Any number less than 1 or 0 or negative numbers are not prime. Then we have n less than equal to 3. I can say that it's gonna be surely a prime number because cases less than 1 or equal to 1 are covered in the above case. And now we have 2 and 3 in this case, which are obviously prime numbers. And for number starting from 5, check something nice. We have um, 5, 7, 11, 13, 17, 19, and so on. A good thing about these numbers is all of them are of the form 6k plus minus 1. 6k plus minus 1 for all values of k greater than equal to 1. Let's see. If k is equal to 1, then we get 5 and 7. If k is equal to 2, then we get 11 and 13, so and so on. So based on that, we can say that we can run a loop for I equal to 5 to I less than square root of n I plus equal to 6, right? Because the numbers of the form 6i plus minus 1. How? Because 5 plus 6, let's see, for I equal to 5, we can check if the number is divisible by 5 or if the number is divisible by 7. How? I is 5 or I plus 2. Similarly, then we go I plus 6 and it becomes 11 or 11 plus 2, which is 13. So that's how we check for all the numbers in the range 5 to square root of n. But now we are specifically dividing the number with the prime number itself, right? So this is a good logic, a better slight optimization over the logic that we have already. Now, in the next section, we are going to implement this problem. So now let's implement the problem using C++. I already have the template code written, and now let's get started. I already have the sample input with me, which is number of nodes, then the tokens for all of them, then n-1 edges, and then all the queries. Now let's see what I'm gonna need. I'm gonna define an n, n, and then for I equal to 0, I less than n, I plus plus. Let's define a token, scene token, and then let's include vector as well. Okay, and vector of int tokens, and then we have tokens dot pushback token, right? So we have stored all the tokens that we have, and now let's store the structure for tree. So now for int I equal to 0, I less than n-1, I plus plus, let's define x and y, scene x, y. Okay, and now we'll have tree x dot pushback y. So we are storing the tree as an adjacency list. Now explanation about this structure, the vector of vector, how we're going to represent it here, is given in my previous video, which was on LinkedIn connections. So if you haven't watched it, make sure you watch that section. If you don't understand this, I'll link it on the top, and then you can continue. So let's continue for now. I'll just define my tree as a vector of, which is an adjacency list representation, right? So I'll define it as tree and the size as n+1. Let's give it as n+1, and then each node, each value in this vector will also be a vector in itself. All right, so we have tree stored. Now we do int q, c in q, while q minus minus for the number of queries. Let's take the query, and then let's make a result. Let's say that we'll have maximum of 1000 elements. So let's make an array and result max n of size 1000. Okay, and now we'll just take the number and output the result. Cout result of x. Alright, so before we solve this query, now we need to actually do the logic that we studied in the previous sections, right? We need to start from the top, go down, then bubble up all the information above to the parent, right? So we're going to implement that using depth first traversal as discussed. So let's call a function depth first traversal, pass it the source, which will be starting with 1, pass the tree and tokens as well to it, and then let's implement this function. So we'll have void depth first traversal int source. We'll have a vector of basically adjacency list of the tree and a vector of int tokens, right? Right, let's implement the logic. So similar, we are at 1. For all the children of 1, we go down. So we go down to 2, and then for all the children of 2, we go down into first of them. So for 2, we'll have 4. So we go down to 4. Now 4 doesn't have a child, so we bubble up, reach 2. For the remaining child we have, which is 2, 3, 4, 5. 5 is the remaining child, so we go into 5, and then so on. We come back and until we traverse through all the nodes, right? So for int child int tree of source, let's do a depth first traversal to this child and tree and tokens. All right. Am I missing a bracket or something? No, right? Why is it then all yellow? Okay, let's continue. Let's see. Let's do one thing. Let's print what where are we right now in the recursion. Oops. Yeah, so g++ 10 code.cpp. Oh yes, we have errors. We have lots of errors. I think I miss a C semicolon or something somewhere. Let me check. Vector int tokens, argument 1 is invalid, template argument 2 is invalid. Okay. I have an angular bracket missing over here. All right. Now for int I equal to 0, semicolon 0 plus. It's correct only, no, here. Line number 23, semicolon before for. Okay. The error is always correct, only we fail to recognize it. Alright, let's give it the sample input that we have. So let's just ignore this 0 for now. So if you see, we have 4, 5, 2, 6, 7, 3, 1. So started from 1, we went to 2, then we went to 4, and now we print 4. Come back, print 5, come back, print 2, come back to the other child of other branch, which was 3. Then again, inside 3 we had 6, so we printed 6. Then we printed 7, then came back, we printed 3, and finally the parent of all of them, which was 1. So that's how depth first traversal works. Okay, and now what we are going to do is, so we are going to do one thing. What we are going to two things, right? What we are going to do at a level, we are going to ask, tell me what are all the children have tokens which are prime numbers, and we'll add that result to the result of the parent, plus we'll also bubble up the results that we already have for the child. So we'll also add the result that is already stored in the child nodes as well. What I mean is, you'll get to know when we implement. So just a moment. So for all the children of the given node where we are right now, what we are going to do is, if isPrime, now we also need to implement isPrime function as we discussed in the last section. isPrime tokens of source, tokens of child -1, then we do result of source plus equal to 1, and source is basically the parent here, and we also add the result of all of its children. So result of source plus equal to result of this particular child, right? So let's visualize this. We'll implement the isPrime function in a while, but let's first visualize this. So 1, 2, 3, 4, 5, 6, 7. We already have that. With now what, when we come down to 4, it does not have any child, right? And similarly for 5, it also does not have a child. Now we come back to 2. 2 has 4 and 5 as its child. The token for 5 is also 5, which is a prime. So in 2, we already have initialized zeros for everything. So in 2 we add 1, and for 2 we have result as 1. Similarly for 3, 7 is prime, so we'll have result for 3 as 1. If we come to 1 now, for 1, what are all these children's? 2 and 3. And 2 has a token value of 2 and 3 has a token value of 3. Both of them are prime. So for 1, 2 and 3 are already prime. So 2 is already there, plus the result of 2 and 3 itself, which is 1 and 1. So 2 plus 1 plus 1, which is 4. That's what we are doing here. That's how we are implementing this logic. So now with this implemented, I think we only need to implement the bool isPrime, which will take a number and then just, so if number less than equal to 1, return false. If number less than equal to 3, let's return true, as discussed in the last section. If number modulo 2 equal to 0, or number modulo 3 is equal to 0, this is to cover 4, return false. 4 and a little additional cases. And then now we start from 5 for int I equal to 5, I less than square root of n, squaring both sides, I square is less than equal to n, I plus equal to 6. Numbers of the form 6 scale plus minus 1. So if number modulo I equal to 0, equal to 0, or number modulo I plus 2 equal to 0, then we return false. So what am I writing? False. Otherwise we return true. All right. So we have isPrime. We have everything written. Let's try to run this code and let's try to run this code and let's see what the output we get. Let's first compile it. All right, a compile error. I should use the name number over here. Okay. And if everything works good. Okay. So as discussed, for 1 the answer is 4, for 2 and 3 answer is 1, and for 4, 5, 6, 7 the answer is 0. So the problem is basically solved, and what I wanted to tell is it's not a very difficult problem. First, see, there are 2-3 things in this problem which are very important. You should be able to understand how to store the given data so that you can be able to retrieve it whenever you need it. Secondly, you should be able to form the logic, seeing the trend in the logic. Just take a piece of paper, write down, make the structure, and see how you go down, and while bubbling up the recursion stack, you go up and then collect all the data from the bottom and then store it in one traversal itself. And some proper visualization can help in that. So that's it for this implementation. If you enjoyed watching this video, give it a thumbs up, and please subscribe to the channel if you haven't, because I'm going to come up with more PoD questions and more solution videos as well. So thanks for watching.